Yesterday we learned what polar coordinates were. We learned how to go back and forth between polar coordinates and rectangular coordinates. Today we're going to go back and forth between polar and rectangular equations because guess what? Next week we're going to graph these. Instead of just graphing points on that awesome graph, we're going to actually graph equations on that awesome graph. So, and today we might graph on the graphing calculators if we can squeeze it in. Okay. There we go. Today we're doing equations. It's nice outside today. It's nice outside.
It's very nice. Looks like it.
There are people out running on the track right now.
We had to be moving furniture and stuff inside and outside the
Equation conversion, same idea as coordinate conversion, same rules apply. We know that x equals r cosine theta. We know that y equals r sine of theta. That's based on our right triangle stuff. What else do we know? We know that tangent of theta equals y over x. We know r squared equals x squared plus y squared. All of this comes from the basic draw angle in. This is r, this is y, this is x. So all of that stuff that we talked about yesterday, remember, is just all from chapter 4. And we just want to convert, which means if we want to write this in polar form, we need to change all x's and all y's to r's and thetas. That's how you know you're done with the problem. Using this stuff. Try to match the back of the book on these. There's definitely some simplifying involved. And we'll talk about that more as we get to some of these. But if I want to convert this, I need to change x. Do I have something I can substitute in for x? With r's and thetas in it? X equals r times cosine theta. So can I change this x to r times cosine theta equals 4? We got rid of the x. We made it with r's and thetas. We like to try to solve for r if we can, and you'll see in the graphing calculator, just like when we graph on a graphing calculator, it's always y equals. When you graph these on a graphing calculator, it's r equals. And so I think it's good practice of getting r by itself. So if I was going to do this on my homework, or if you checked in the back of the book on your homework, this would not be the answer. They would get r by itself. So do you agree that I could divide by cosine here? And I would get r equals 4 over cosine theta. Could I do anything else to that to simplify it? We don't usually leave cosine in the bottom of a fraction because we could bring it up and we could make it 4 secant theta. And if you check your answer in the back of the book, that's what they would have. And so you just want to try to get in the habit of trying to simplify it and trying to match the answer that they have back there. I was talking yesterday about how polar coordinates sometimes make things easier to graph. What does a graph of x equal 4 look like? Just a vertical line through 4 on the x-axis. This is much easier to graph using what we normally graph than graphing this. So that's why normally we don't graph lines with polar coordinates, because this looks much uglier than x equals 4. But some of the other equations will be nicer with polar coordinates. Okay, on your homework today, a lot of them say graph, but you get to ignore those directions today, and we're not graphing it until next week. So, good news for you. Again, when you're trying to write this in polar form, we need to change x and y's with r's and thetas. So do we have something we can plug in for x? R cosine theta. Can we have something we plug in for y? R sine theta. So we're just going to plug them in. So this is r cosine theta times r sine theta equals 16. And then it's just simplifying from there, trying to somewhat match the back of the book, or trying to at least isolate r a little bit by itself. So for me, when I did this one, r times r is r squared. like, even if we weren't graphing on a calculator, when we graph equations, if we're going to make an XY chart, it's so easy if Y is on one side, because that means you can pick X's and plug them in and get Y's. The same thing with this. When we graph these by hand, it's much easier if we can have R on one side, because then we can pick theta values and plug them in to get the R's that go with it. So that's why it's good to have it to practice this. So do you agree that I could divide this over to the other side? And am I going to leave that as 16 over cosine theta, sine theta? Because I could pull those up and make it 16 secant theta cosecant theta. And that's a decent answer. If you were going to graph this on the calculator, you would have to get R by itself, which means what else would you have to do? You'd have to square root it. If you didn't square root it, I always say try to at least get R by itself on one side. If you left it squared, like, that's okay. But you could square root both sides, and you could say this was the square root of 16 secant theta cosecant theta. But I like this answer better, so I think I left my answer like that. Trying to think. I feel like when we're talking about R, this R is in terms of the radius, and I feel like the radius should always be positive. But we'll have to look at the graphs to answer that question for sure, because maybe we do need plus or minus. I don't know. I think that's why I keep it squared, so I don't have to think about it. But maybe I'll mess with the graphing calculator right now and figure it out. Let's see if we should do plus or minus while we look at the next one. Okay, sorry. 16 secant theta cosecant. Look how fun this one looks.
How many examples are there?
7,162. I hate when people ask how many examples are there. I never tell you. Do you know that? Have you ever realized that? I always know. We did that in college algebra one day, I think, because was it college algebra that we did that, or was it this class? I think it was college algebra, because they decided they wanted to see it, and then the funny part was I had blank slides at the end and I didn't even remember, and so it totally psyched us all out, because I was like, oh, 3 more slides, and then we got to the homework because I just had blank slides at the end that it counted.
I think it was like 8 total.
And then the homework came up on like the 6th slide, so yeah. Okay, sorry. What do you think we should do on this one? Cry? Well, no, because you can't break up addition under square root. It would be awesome if you could, but you can't. So if we square rooted this, nothing would happen right now because you can't break up the addition. Like, you can't take the square root of this separately from the square root of this. Like, it would all just be stuck under there. Here are some options. One option is we could FOIL it out first and see what happens. The other option is we could try to plug in x cosine theta and, r cosine theta and r sine of theta and then FOIL it out. But at some point we're going to FOIL it out. I think it's going to be easier to FOIL it out with x's and y's or change them to r's and cosines. And I think x's and y's. So I think FOIL away, my dears. Yeah, Deborah, I think we need plus or minus. Because if you don't do plus or minus, you only get half of it. So there you go. Remember when you FOIL this? That it's not just x squared plus 9, right? There's a middle term there. X squared plus 6x plus 9 plus y squared plus 6y plus 9 equals 18. With me on that? And it works out really well that the 9 plus 9 is 18. So is that going to just subtract and cancel out with the other number over there? So I get minus 9 minus 9 minus 18. I'm left with x squared plus 6x plus y squared plus 6y equals 0. center at -3, -3. A radius of the square root of 18. That's ugly, but it's a circle. From here, there's definitely places to go. This shows up a lot. Definitely going to be on your homework today. Definitely could be a homework quiz in your future. Definitely going to be on your test in your future, because I like to make you do these circles. Because every time you have options. You could go through and replace every x with our cosine theta and every y with our sine theta, but there's a better choice. Do we know what x squared plus y squared equals? R squared, because it's Pythagorean theorem. Which means, just like we can say sine squared plus cosine squared equals 1, and that's always a great one to put together, when you're doing these,
R squared plus 6x plus 6y.
are you being facetious back there? Yeah. You're like, oh, that makes sense. Like you're being very sarcastic.
No, I was being serious.
Oh, okay.
No, I'm surprised.
Oh, okay.
It's like that.
It made sense. Okay. I thought you were just being like, because you weren't here yesterday and you were just making fun
I
of
was
sarcastic. So x squared plus y squared equals r squared, and I'm going to go ahead and replace both of these with the r cosine and the r sine, because here's what I always hate when I grade a test. Your problem is not finished if you have some r's and some x's and y's still in the problem. Like if you're going to polar form, it can't have x's and y's in it. So make sure you're going through and you're replacing those. From here, it's just simplifying it, and that's where checking your odd answers tonight, check them to see what they have, so if you can see how to get that. Even answers, you don't have those to check, but you can use your other answers to kind of, trying to get r by itself as much as possible. Anyone have a suggestion? We could pull an r out. It's equal to 0 even. Could we divide an r out? That seemed not allowed. I think we could too. I divided an r out. Can I do that? I'll just put a big giant line here and put divide by r. So that makes r plus 6 cosine theta plus 6 sine theta equals 0. And now is it pretty easy to get r by itself? We just subtract those other things over. So, sorry, I think that would be r equals -6 cosine theta minus 6 sine theta. And I had my answer like that, and I think when I checked the book, they factored the -6 out. And as long as you can kind of see what they did, that you can match that up. It's where you might have some multiple choice on this test more than in the past, because the multiple choice kind of makes you simplify the way they do. Mason tried to convince me that I should give him all the even answers, so he could check his answers on the even ones also, but I didn't fall for it. But good try. So either one of those would be okay. And again, that makes it easier to graph, which is why we do that. I think maybe the next one is going the other way. If they give us the polar graph, can we write the rectangular? Oh, it is. I think this is a little bit harder than the other way around, because on the other one, every time you see an x and every time you see a y, you can plug in just like yesterday. But on this one, you have to be able to replace stuff in. And there's more than one way to do these. But again, keeping in mind that we know x equals r cosine of theta, y equals r sine of theta, x squared plus y squared equals r squared. Those are just kind of in the back of your mind all the time. We can't do a direct substitution right now because we don't have any of that, doesn't match any of this. But if you could solve something so that you could do that, you could plug in, it's an equation. If you could multiply by something to make it match up, you could do that also. So when I see this problem, not the only way to do this, but when I see this problem, I think if I had an r cosine theta instead of just a cosine theta, I could just replace that with x, right? So how can I make an r come in there? It's an equation. Can I just multiply by r as long as I multiply this side by r too? You can do anything to an equation as long as you do it to both sides. And so, look what I have. R squared equals 2r cosine theta. So I have to make it match something that I can substitute. With me on that? So now what can I replace r cosine theta with? Can I replace r squared with something? Is that rid of all of my r's and thetas? That's in terms of x's and y's? Yes. Here's where the book gets a little out of control, and this is where I say you, yes.
So that's what it means when it says convert to rectangular equation, you just have to put it in there.
Yes. Rectangular is what we've always worked with, x's and y's, and polar is the new stuff. So yes. Convert to polar means make it r's and thetas. Convert to rectangular means make it x's and y's. Here's where the book gets out of control because they assume that you all remember how to make this look like a circle equation, because it is a circle, because it's x squared and y squared. This is where I'm okay if you don't do this, but I just want to show you in case you want to know where the back of the book gets this. If we should have time to at least do some of chapter 8, which is conic sections. We'll review all of this. But they just assume that you know that you could subtract 2x over here, and then you could leave space, and you could add y squared. And if you're writing the equation for a circle, you have to make this a perfect square. So you have to complete the square. If any vague memories of doing that when we were doing conics, because you had to make it match up. And so you just complete the square. So half of -2 is -1. -1 squared is +1. So you add 1 over here. And the back of the book would say the answer is this, because this tells you how to graph it. It tells you that it's a circle with a radius at 1 and 0. Sorry, a center at 1 and 0 and a radius of 1. I'm okay if you don't do that. If you want to do that, I'm fine with that also. But I've never made kids do that because I don't want to waste the time of reviewing all that completing the square stuff right now. But that's where it comes from. So just be aware on the ones that are x squareds and y squareds, unless you complete the square, you're not going to match the back of the book. Okay? There you go. How many more examples did I say we had?
7,000.
Dang it, only 7,000. I forget the number. I wish I could remember the number I make up when I say that, so I could subtract the ones we did. No more WWE. We don't have time. We're supposed to do calculators today, and it's Pride Time Day, and we're never going to make it. Chloe's about to leave. What can we do on this one? Maybe. Is secant something that is in one of the little equations I gave you? No, but what could I change secant to? Oh, could I write this as r equals 4 over cosine theta? And what could I do with that cosine? We could, I guess. Oh, what if I multiply this over to this side? Does that work? It's not wrong. You can multiply r in. I promise it's still, like, it will still work out and you'll just have more stuff to do. But I think, look at the number 1 that we did. Was number 1's answer r equals 4 secant theta? Oh. I always try to put my cosines and r's together if I can, because then I get r cosine theta equals 4, x equals 4 is the answer. So the only good thing about having to do both of these is sometimes you can use one to help you go backwards the other way. Maybe in second hour said x equals 4 as soon as she saw this because she had her other one. And I was like, man, that's some good thinking there because she knew right away that it was one we done already. Want to do a harder one? I know you do. This one looks so similar, right? You want to do the same thing.
Just long. It's like when you get to our birthday, it's like, whoa, this is what we did on our notes.
The difference on this one is secant's already on the same side as it, so r and cosine are not together, right? What do you want to do? Cry. Might answer all of them. Leave it. Yeah, if I have a fraction, I'm going to move it over. similar to another one that we did when we had r and then just cosine. What did we do to make the be r cosine? Multiplied it in r, right? And so now this is going to be very similar. I think it was number 4 that we did this. We say now let's multiply an r in, and now I get r squared equals 3r cosine theta, and I can say x squared plus y squared equals 3x. And again, that's where I would just leave this one. This one's a lot uglier than my last one with the circle, because now you got to complete the square with a fraction, so you're going to have to take half 3, which is 3 halves, and then square, which is 9/4, and who wants to do that nonsense? No one. Then we have the graphing calculator. What is this nonsense? Sine of 2 theta. Oh my gosh, am I supposed to remember all those identities from chapter 5? Oh man. Here's the good news. I'm not going to give you any of this on a test that would make you remember that identity. Because first of all, I gave you that identity on the test. But the book likes to throw those in every now and again. So there might be one in your homework that is an identity that you have to look it up. There's a calculus problem every year. It's like chapter 2 that they throw something in like that. And I find it ridiculous that they expect that you're going to remember that in calculus because you just took a test last week and you already forgot it. So, the book is mean sometimes. But I'll tell you what it means. It is sine of 2 theta is 2 sine of theta cosine of theta. If I was going to give you one on a test, I would start there. I wouldn't make you do that first step. And now you have options. You have to be able to plug in for x and y. So there's more than one way to do this. It's just what way you see. Anybody see anything? R squared, because we replace that with x squared and y squared. What about these? What can we do with this? This is what we know. So I'll tell you, there's 2 ways. I did it one way, and in second hour, someone suggested another way. Someone suggested, well, could I multiply by r 2 times? Could I multiply an r here and then just multiply it over there? Would that work? That works. It makes perfect sense with what we did. So we could say, well, let's multiply r squared, and then throw in an r here and throw in an r here. And again, as long as you do it to both sides.
So your way is that?
That was Colin Berry's way.
Oh, there, yeah.
And I said, hey, let's see. I think it'll work. Here's my way. Instead of multiplying in, because I already had r squared so perfectly over there, I said, well, instead of putting r in, could I solve for sine here? So could I say that sine equals y over r equals sine? So I replaced sine and cosine with y over r and x over r, and I multiplied it over, and I got the same answer. But I think Colin's way maybe makes more sense with what we've been doing than my crazy way. So I'll go Colin's way. Because now I have 2r sine of theta, r cosine of theta. His is more direct substitution, I think, than my crazy way. Can I replace this like this? And what can I do with r to the 4th? Yeah, because isn't that like r squared squared, right? Or just do it twice. X squared plus y squared times x squared plus y squared. It's the same thing. So x squared plus y squared. I squared this, but you could just write it twice. 2yx. The good news is you don't have to FOIL that out. This is a crazy graph. It's nothing that we've ever graphed before. Maybe even like a crazy rose curve kind of thing. If I remember correctly. I forget. We're going to learn what all these equations are later on, but I don't remember off the top of my head. No. We have other stuff to do. So the first 4 on your homework today are like the first you're supposed to match the graph with the equation, and so I wanted to show you how to do this on here. So let me have you write this down, and then we can look at the first four. So 31 through 34, you just match the graph with the function. And I just want to show you the calculator stuff. And then the rest of these, make sure you understand that the directions say to graph these. That's because I think they're pretty sure that you all have graph calculators with you at all times. And we don't. So you don't have to graph on your homework. So just be aware of that as you're doing your homework tonight. So write this down, then open your book to 540 so we can do these first couple on the calculator. So the big thing is go to mode again like we did last time, and you got to go to polar mode now. Some of you might already be in polar mode because you got the calculator from second hour. Angel, did you give Taylor one of those?
Oh, I'm sorry.
I'm sorry. Let me turn mine on. And first thing, go to mode. Make sure you're in radians. And the big thing on the test, there's going to be part of the test that I let you use a graphing calculator. You got to know how to use your calculator and have it in the right mode. Because if you come to me during the test and you say, my calculator didn't work, I'm not going to put it in the right mode for you. So that's why we're going to practice doing this today. Make sure that you turn these off when you're done with them. They do turn off eventually on their own, but they take 4 batteries and they really suck the life out of them. Go to mode. I'm already in polar mode, but parametric, polar, you'll know you're in the right mode if you go to y equals and it says r. Because r equals something with theta. I think I graphed the second one, which kind of gives you the answer already. But you want to make sure you can get this to work, and the window is the most important. So let's do 31. Says 5 cosecant theta. How do you write cosecant on your calculator? Yeah, 1 divided by sine. Or since it's 5 cosecant, can I just do 5 divided by sine? I mean, or you could multiply by 1 divided by sine, but I think you can just do 5 divided by sine. And notice when you hit x comma t comma theta comma n, it does theta now. The window is the most important. R is going to, theta is going to be trig values, and then they still give you an x and a y axis. So just so you know, if you go to your window, I think you should do negative 2 pi to 2 pi. I don't really think it matters what the steps are. And then I just did a minimum and a maximum of 10. I think that should give you plenty on there. But really important that you go from negative 2 pi to 2 pi, because if not, it won't give you all the value. But this should just be a straight line when you graph it. Right above that. Alright, so it should be a straight line, and then you just need to do the first 4. I think I just did the first 2 for you. You just match them up, and then you can see how you can get those cool little graphs. But if you don't get it to work, let me know. And then when you're done with those first 4, you don't need a calculator anymore. I think make sure that you use this button and not this button. Because if you do subtraction, it just errors right away. Second on is how you turn it off. So that means there's a window range error with your window. So that means they're telling you the error is somewhere in your range. So go to your window. Your min and your max are the same. So saying if you went from negative 10 to negative 10, so it can't graph that if you do that. The nice thing about these calculators is they